Hello, welcome to our GR1089 Section 10 webinar. Thank you for joining us today. This webinar is being given by MET Laboratories. MET is a leader in the testing of electrical and electronic equipment for environmental hardiness, product safety, and electromagnetic compatibility. MET operates world-class labs in Baltimore, Maryland, Santa Clara and Union City, California, Austin, Texas, and also runs operations in China, Taiwan, Korea, and Italy. This webinar will run about 30 minutes with an additional 15 minutes for questions and answers. Due to the number of registrants, all attendees will have their phones muted. If you have a question, please type it in the questions area of your control panel. We will attempt to answer all questions at the end. If you are having technical difficulties, you can contact us the same way, or if you can't, call us at 410-935-6053. That's 410-935-6053. And we will try to resolve any problems quickly. Just a quick note on upcoming events. This month, MET is hosting a number of exciting things. Next week, on September 13th, is our big annual Global Product Compliance Seminar and Crab Feast in Baltimore, Maryland, featuring TCB Council Executive Director Chris Harvey. And then the following week and the week after that, we have two wireless testing seminars, one in Silicon Valley in California and one in Maryland. You can register for any of these events or other upcoming seminars and webinars on www.metlabs.com. Today's webinar is being presented by Asad Bajwa. Asad is director of MET's EMC lab. At this point, I will hand over the presentation to Asad.
Thank you, Banavi. Hello, everyone. As Banavi mentioned, my name is Asad Bajwa. Today, we will be exploring some of the changes done with the release of issue 6 of GR1089 with a special focus on Section 10, and we'll go have an in-depth discussion about some of the requirements which are covered under voltage and over voltage transient tests. Here is the brief outline of my presentation. We'll do a quick comparison between the ANSI document and the new ATIS document in the light of the release of issue 6. We'll go over under voltage, over voltage requirement. We'll talk in depth about the generators used in testing today. What are the challenges there? Very fast rise time, fall time, the overshoot, so on and so forth. So we'll have an in-depth discussion there. We'll talk about the verification, how the generator verification takes place, what are the options out there, what are the limitations, what are the technical difficulties there. So I will take a few moments to very quickly talk about some of the changes which happened with the release of issue 6, only about Section 10, and then we will jump into our main topic, which will be the test generator for under voltage and over voltage testing. Okay, Section 10 basically. Several modifications. The very first modification is the addition of the criteria, which is added as criteria 10.3, the over voltage requirement. With this new requirement, the units has to operate under normal conditions with 30 minutes at the maximum voltage specified by the ATIS document for the operating voltage of the device, whether it's a 48 volt or 24 volt system or whatever that may be. Next change is the which is documented as Section 10.4 over voltage transient. This is not necessarily a new requirement in the industry. This requirement has always been there as part of the AT&T requirements for DC systems as part of the AT&T verification document. However, as an effort to harmonize the requirements, now they have added this requirement to 1089 Section 10. Basically, the idea is that the device has to operate at minus 48 volts. Then, with the slope of 10 volts per millisecond, it goes to minus 75 volts. Stay at minus 75 volts for 10 milliseconds, and then following the same slope of 10 volts per meter, it goes back to minus 75 volts. And during this time, the device has to continue to operate. Again, this is somewhat challenging considering if one is testing the high current system, which we in the lab environment see almost every other day. Folks are coming up with the designs which would easily draw 350 to 500 amps system, and we've been in discussion with some of our customers whom are planning even higher power system, and we are gearing up to enhance our capability to test the system, which could range for, which could go for the range of current at 48 volt DC from 700 amps or higher. So we are getting ready to be able to test those systems for these waveforms. Now the other thing is the Section 10.5. This is more of, in my opinion, editorial change. It's not necessarily a technical change. For the folks who are well familiar with the 1089 from issue 4 to issue 5, Section 10 clearly listed under voltage, over voltage, and impulse waveform tests as separate requirements very clearly as in the body of the Section 10. However, with the release of issue 6, they removed all that detail and just put references to the ATIS document, which basically replaces the NCT 1.315. So we will see all the references to under voltage, over voltage, and impulse transient as per in Section 10, going back to the ATIS document rather than providing the detailed description separately. The next change is the Section 10.6. The main change is twofold. One, the limit has to be based on 10 amps rather than 1 amp. When we do the calculation based on the formula given in the standard, the assumption up to issue 5 was the minimum limit. The limit will be based on minimum current of 1 amp. Now, with if the equipment draws current less than 10 amps, then the limit will be based on 10 amps. In other words, this favors the manufacturers. Now your limit is much higher, and the probability of your product meeting this requirement is much higher. Second change is the addition of the high impedance transducer. I will explain that in next 2 slides. My next slide shows the circuit diagram of the system to measure the noise coming from the telecommunication equipment using a combination of the inductors and the capacitors. However, if I may point out, the capacitor C1 and C2, these capacitors were not recommended in the circuit provided in NCT 1.315. When NC documents was superseded by the ATIS document, the ATIS version then added these 2 capacitors, which are, in my opinion, extremely critical to avoid any short circuits, because without these capacitors, if one accidentally shorts the body of their coaxial cable, the shell of the coaxial cable, which could be either a BNC connector or N-type connector, depending on what cable combination you're using, if you accidentally drop that on the ground with your DC system reference to the ground, you can cause extremely huge spark, which basically kind of looked like a welding burn on the floor. So those kind of safety issues were resolved with the addition of these two capacitors, and system was already very safe. However, if you go back to the time when Section 10 requirements were not there and testing was being covered for, especially for AT&T, by the AT&T checklist, large number of the labs were using the spectrum analyzer, low frequency audio spectrum analyzer with very high input impedance, which will range up to 800 to 1 megaohm. Ideally, people were using the spectrum analyzer with 1 megaohm input instead of the 50 ohm input, which we see on large number of these spectrum analyzer being used in the industry today. Now, with this requirement being added to 1089, with the addition of the references to, with the switching of the references to ATIS instead of T1.315, there've been ambiguity based on the standard whether labs should go back to 1 mega ohm as was the common practice in the industry in the past, or shall they go with the 50 ohm system. So some labs went with 1 mega ohm, some labs were using 50 ohm spectrum analyzer. Long story short, you will get different results depending upon what will be the input impedance of your instrumentation. In my opinion, with the release of issue 6, they try to clarify that ambiguity so that everybody is doing the testing for noise in a consistent manner and results are repeatable if one goes from one lab to the other. So my next slide shows, I borrowed this diagram right out of the 1089, where we can see right next to the capacitors C1 and C2, we have a high impedance transducer. This transducer could be a separate board or a device which could hook up to your noise measurement system, which could very well be a spectrum analyzer with 50 ohm input or not. In some cases, some of the Agilent spectrum analyzer models, they already give you the built-in option where you can choose between 50 ohm and 1 mega ohm impedances. I highly recommend the use of those spectrum analyzer which have the built-in feature of 1 mega ohm for the consistency sake. The next change is more of the documentation related change. This go back to some of the changes in section 1 where it been mentioned to have all the documentation necessary for the product, the labels, the user manual, the installation manuals, any other instructions related to the operation, ESD, so on and so forth, to be provided as a package with the documentation when you are putting this product on the market. So on the same note, this criteria 10.8 is saying clearly list the nominal voltage range on the product label, and that label needs to be in a visible area, and it should not be easily removable label. Whether it's a label or a faceplate, it needs to be very, very clearly visible. So this is another documentation change in 1089. At this point, I want to jump into the main topic of this discussion, which is the undervoltage and the overvoltage. Before I go there, just want to mention, in addition to undervoltage, overvoltage requirements, there is a third requirement, which is the impulse transient requirement. I purposely did not include that into this presentation because that has been a very well established test method for several years. There are some minor challenges when it goes to testing the higher currents. However, a standard clearly defines the options using transformer or inductors to tackle that situation rather than using the resistive circuitry or resistive network for the currents higher than 25 amps. So I'm not going to focus on the impulse. My main focus will remain on the under voltage and over voltage. Why? First question is, why are we worried about under voltage and over voltage transients? The main reason is that we are talking about switching very high load currents of the order of a couple of hundred amps to 400 amps in practically zero time. Again, let me rephrase myself. In practically zero time, and what it means is the DI over DT would be outrageously high, which will lead to numerous problems, and we'll explore them as we go through this presentation. At the same time, it's not a simple task to achieve switching that higher load currents in the time frame of the 5 microsecond or 2 microsecond, which is required for the over voltage transient. So basically, this slide is giving a summary of the under voltage requirement. Nominal voltage is minus 48 volts. For before I describe that, let me go to my next slide where we can look at the waveform, and I can describe these parameters when we are looking at the waveform. So this waveform is basically showing that we have a minus 50 volt system. The device normally operates as minus 50 volts or 48 volt. The voltage need to switch from minus 58 volts to minus 50 volts to minus 5 volt with a rise time of 10 microsecond. It has to stay at minus 5 volt for 10 milliseconds. Then within 5 microseconds, it has to go back to minus 50 volts. Minus 10 the 10 microsecond rise time from minus 50 to minus 5 volts is already a challenge. However, going from minus 5 to minus 50 is even a bigger challenge because the duration of the time. And this waveform is a representation of an ideal waveform. However, due to the lead inductances, however, due to the parasitic capacitances all over the place, the way the system is designed, the way the cables are routed, so on and so forth, there will be overshoots all over the place. They will be overshoot at the rising edge. They will be overshoots at the falling edge. And the biggest challenge in designing and in achieving these very short rise time and fall times at the currents of 200 to 400 amps is to manage the overshoots and undershoots. Again, please allow me to re-emphasize the point. Switching something from in 10 microsecond or 5 microsecond or of the order of nanoseconds is not that big a deal. What makes this thing a huge problem is switching these, switching in these times at 400 amps or higher. This is the over voltage transients. Same situation where we are going from minus 50 volts to minus 75 volts. The challenge is even bigger because now the rise time has to be less than 2 microseconds as is shown on the next slide. The time from minus 50 to minus 75, we need to reach there within 2 microseconds, actually less than 2 microseconds. However, the rising slope, if I could call that rising slope, the way it's being shown on the screen, is 10 volts per millisecond, which is not that big a challenge. However, there are some of technical difficulties which I will elaborate in my next few slides. What are those difficulties are? This waveform gets more complicated compared to the under voltage, especially due to the fall time of 2 microseconds. What are the problems out there? What are the main concerns there? The biggest issue is when this standard was written, there were no commercially available systems or solutions. There were obviously programmable DC power supplies which could provide switching to 400 amps, even 1000 amps. MET Labs and many other labs who are in the telecommunication business who offer the services. They had those power supplies, programmable power supplies available. Unfortunately, almost all of them have, even the fastest one out of those models available today, have the minimum switching time of 12 microseconds. So keeping in mind the minimum switching time of commercially available system, which can switch at 48 volt DC, about 400 to 500 amps, they require 12 microseconds to switch from minus 48 volts to 75 volts or minus 5 volts, depending upon which waveform we are talking about. That made those power supplies practically useless. So all the labs were scrambling to figure out a way to resolve this problem, because this requirement has become mandatory, and all the labs who provide GR1089 service, they have to come up with a solution to implement that. So we work with our partners. I'm very thankful to our partners in the industry who supported us, working with us to finally come up with a solution which can provide us the capability at 48 volt DC, where we can do 400 amps without any trouble. I'm thankful to the folks at our partners at Juniper, who also supported us during the building of this generator. We got very valuable feedback input from them, and I'm really grateful for their feedback and their support while we were building this generator. Now, let's look at, in a nutshell, in a summary, what is the generator supposed to do? The under voltage or voltage generator. Idea is that transient generator would normally be providing minus 48 volt or 50 volts to the device under test. Say device is drawing 400 amps. So generator needs to be capable of providing a steady state current of up to 400 amps, considering the EUTs we've been testing in the industry today. At the same time, this generator has to be capable of providing the voltages down to minus 5 volts or as high as minus 75. If we consider the tolerances for the over voltage, there needs to be the flexibility in the generator where the over voltage, output voltage could be adjusted from anywhere from minus 75 to minus 95 volts, because that is the tolerance requirement by the standard. And in my opinion, not only the range needs to be a lot more wider, because if there is a problem, the device is failing at minus 75 volts, then the lab need to be able to reduce the voltage from minus 75 to say minus 60 or lower in a way that we can help our customer identify what the threshold is, which will allow us to identify what is the root cause of the problem if there is a failure. So let's explore how we came up with this generator. Before going there, the standard talks about how to validate the waveform. That validation description made the things more complicated. When the time several years ago, when this requirement was not part of 1089, before issue 4, I believe up till issue 3, this requirement was not part of 1089. Folks were just following AT&T document to implement some of those requirements. The challenges were that the tolerances were the same, which we are looking at today. Then how come people didn't have to worry about the tight tolerances we are looking at today? In my opinion, the main reason there is that those documents at the time when this requirement was not part of the 1089, those documents did not mandate generator verification or a calibration method. However, the difference is the current version of the 1089 refers to ATIS document, and ATIS document very, very clearly states 4 different methods to verify the test generators. And when we explore these methods of verification of the test generators, we will see how complicated it gets. First method sounds very simple. It refers to the test generator as a power amplifier. it's assuming the generator is basically a very wide band power amplifier, which would cover the frequency range as low as from DC all the way up to hundreds of kilohertz, if not the megahertz, because we want to achieve very fast rise time and the fall time. So it says determine the rise time, determine the fall time with the open circuit, determine the slew rate, so on and so forth. All those things are extremely complicated and extremely time-consuming way to validate the test method. And you still do not get a clear picture how the generator would behave when it's hooked up to the actual load. So large number of folks, large number of labs in the industry would not use that method. It's practically very, very difficult to use that method. Method number two sounds very simple again. That hook up the generator, like I showed in the previous slide, and I will go back there to talk about that. Hook up the generator to the UT, and the point where the power, the UT is hooked up to the transient generator, assuming we are connecting it with 1 meter leads as specified by the standard, verify the waveform parameters, rise time, fall time, 10 millisecond duration, so on and so forth, for both under voltage and over voltage. Imagine the input impedance of a unit which draws current close to 400 amps. It will have huge capacitances, inductances. Considering those capacitances and inductances have been hooked up at the output of a switching device, anybody who's familiar with the switching and the way the capacitors and inductors work will know connecting the real impedance across any switching device will drastically change the waveform parameter. That's exactly what happens. So large number of generators in the industry would not or cannot be possibly verified using this method. And standard clearly states all these methods are not equal, meaning if you validate your generator with a resistive load, that does not mean that your generator should also be validated, should also automatically be validated by the method 1 or 2 or 3. These methods are not equal. So if you are validating your generator with method 4, that does not necessarily mean that it also complies with the other validation methods or vice versa. So moving along, the method number 3 is a resistive load in series with the capacitance, and standard specifies using a 1700 microfarad capacitor. Again, using this method leads to serious problems. Waveform drastically gets cluttered, and you do not get a real picture what is the output of your generator. The third method, sorry, my apologies. The final method, method 4, is more appealing, where standard is saying using the resistive loads, and standard specify our table. In a nutshell, the idea is that to use a resistive load comparable to the steady state current drawn by the EUT, and using that method validate the rise time, fall time, duration, and standard says in addition to that also provide the actual waveforms when the EUT is hooked up with the generator. So it's a little bit extra work, but this is the most practical, meaningful method of validation the test generator. Now, how this generator works? How come the generator we came up with is more unique and more accurate, in my opinion, compared to the generators being used in the industry today? Our generator is based on, I will start from left to right. The red box, which is labeled as mystery switch, is a very high-speed 400 amps switch, which acts as a single pole double throw. To give you an example, however, it's an electronic switch. It's not a mechanical switch. It's extremely difficult to find mechanical switches which could operate at these fast rates. So using an extremely high-speed electronic switch with the current handling capability more than 400 amps, we hooked up two power supplies. One power supply which can provide up to 500 amps at 48 volt DC. Other power supply which can provide 75 volt DC with the adjustable output, which could take us anywhere from 0 all the way up to 300 volt DC. We hooked up that power supply to the other input of the single pole double throw switch. We combined the returns of those two power supplies. The output of the generator basically is the output of the single pole double through switch, which will be hooked up to the load. Now, how this thing works? There will be a timing circuit which will precisely control the timing, how and when one switch of this MOSFET switch closes and the other one opens up. Due to the copyright issues, I cannot elaborate on how the timing circuit works, what is inside the timing circuit. I can just simply say that the timing circuit is also the heart and soul of this generator, which cleverly times the switching and the dead bands between turning on and off the power supplies from 48 volt to 75 volts. The other bigger challenge is if you look at the amount of energy. Let's go back for a second to the overvoltage waveform. The overvoltage waveform goes from -50 to -75, meaning 25 volts. We are having a delta of 25 volts within less than 2 microseconds. So that would require a tremendous amount of energy. How can we provide that practically infinite amount of energy so that there is no inertia which would lead to slow response, which hinders a designer to go from 50 to 75 volts in less than 2 microseconds. So that I have indicated as a black box. My apologies, let's go back. Some techniques we use to provide and source additional energy, tremendous amount of energy, and it costs tons of money to be able to arrange, make that arrangement which will provide that extra energy to the 75 volt power system, which will enable us to switch from 75 volt to 48 volt. In addition to these challenges, the other challenges are the wave shaping. Close to the red box, which is marked as switch, I have labeled 2 wave shaping circuits. These circuits are a combination of resistor and capacitor. They not only help us get rid of the overshoots, they also help us achieve the correct rise time and fall time. In addition to that, for the overvoltage waveform where the rise has to be 10 volts per millisecond, we have another combination of a diode and a resistor-capacitor combination. Please keep in mind that resistor-capacitor combination, which is close to the load, basically it hooks up in parallel to the load, will have to be tunable, which could be basically, in other words, mean selectable with a switch, basically a bank of resistor and capacitor, which could be selectable with mechanical switches. So your generator has to have the flexibility to tune these networks according to the amount of the current being drawn by the UET. So these wave shaping networks are cannot be designed in a way that you choose one value and leave it there. These are the ones which are the parameter or the function of the current. So if your current is in the range from 50 amps to 100 amps, you may have one setting. You're going from 100 amps to 200 amps, you may have another setting, and so on and so forth. So you may have to have 3 or 4 different settings of these wave shaping networks, which will allow you to get the cleaner, clear, correct waveform according to the standard. Talking about the design challenges, parasitics was the biggest challenge. We learned the hard way that depending on how we route the cable, depending upon what the length of the cable to hook up one component to the other, the layout of all these boxes and pieces, the way we package them, that was extremely critical. It requires a lot of tuning. High current switching added to a lot more complications. Overshoot was another big issue, so we have to come up with clamping circuits to get rid of the overshoot. In addition, we have to come up with the some sort of protection devices at the very output of generator, because depending on the actual real impedance of the EUT, it could cause very high spikes, which can literally damage the switches, the high-speed single-pole double-throw switches we are talking about. And finally, the biggest challenge was the amount of energy needed to make the changes happen, especially for 2 microsecond switch from 50 volts to 75 volts. Another challenge had been the noisy power supplies. We've been using commercially available power sources for 48 volt DC and 75 volt DC. Especially the 48 volt DC system, if used 48 volt DC power supplies off the shelf, if they are used as is without any treatment, they cause serious problems. Waveforms are never clean. Even it becomes a challenge to get the correct waveform. However, with some special techniques we used, we managed to overcome this problem, and we were able to clean up the noise and get the right waveforms. That's basically concludes my presentation. We talked about some of the changes in Section 10. We talked about the challenges with the undervoltage, overvoltage waveform, rise time, fall time, noise, overshoots, and finally we were able to overcome all these difficulties. And once again, I want to thank our partners and supporters. With their support, we were able to overcome these problems, and we have a working solution in the lab for quite some time, which is helping us test the products up to 400 amps. Barnaby, back to you.
Yep, thanks, Asad. That concludes the presentation portion of the webinar. A copy of this webinar will be available on metlabs.com. We will send a follow-up email with a link to this file. Now we will answer any questions. If you have a question, please type it in the questions area of your control panel. For questions we can easily address now, we will read the question aloud, then give the answer. Please give us a minute to get oriented with these questions.
Okay, there's one question about the impedance of the high impedance transducer. And again, just to mention that this is a recent addition with the issue 6. The idea of that to have consistent results from one test setup to the other setup, and the recommended impedance of the transducer by the standard is 1 megaohm. The second question we got is that, and I'll read the question, which portion of the testing we have seen most failures? We have seen failures across the board. We have seen failures with the noise testing. However, more of the failures we are seeing are with the large percentage of the failures we are seeing are with the over voltage transients, because majority of the boards component designed for telecommunication system, they are designed, again, I'm being very general. Generally speaking, they are designed in a way that their protection will operate around, say, 85 volts. And whenever there is a voltage present on the DC bus which goes beyond 85 volts, they're going to shut down to protect themselves, and the system will indicate a failure. Looking at the tolerances at over voltage waveform, the tolerance is from 75 volts to 95 volts. And due to the overshoot issues which many generators have, we very often see that people, even when a generator is within the range of the tolerance specified by the standard, they would still fail. So we have to take extra caution to tune the generator in a way that we could stay as close as to 75 volts, not going towards the upper extreme, which is 95 volts.